most of you are professionals of mathematics. You understand all this, so I prepared the talk for very simple students. But I was saying that I thanks very much to Eugenio and Federico for these 20 years of DiferenciaHable, which is a seminar of geometry in the faculty. And so it says very fast, 20 years. But it takes a lot of work, a lot of hard work to carry on the seminar for so long time. So it's really, thank you very much for that. And I choose the topic because this was one of the first, how to say, when I met Federico, he was very interested in this topic of, which is conformal geometry and dynamics. So I should use conformal in the talk because otherwise it's very open, very wide, and it's only conformal geometry and dynamics which I'm going to talk. And Federico was interested at the beginning of his mathematical career with the topic, and that's why I choose to say some things about that. And in this conformal dynamical theory is the Sullivan dictionary. I don't know if you know Sullivan, Dennis Sullivan, which worked in this topic in the 80s or so, more or less. Maybe it's more interesting if Federico could tell us why he moved from dynamics to singularity theory. I don't know. But okay, I'm going to continue with it. And so there is a junction or a framework between two topics, which is the left one is the rational maps on the sphere dynamics. On the right hand side is the finite groups dynamics. So this is the topic of the talk, and this is a representative of those of this situation. And so this framework, which creates Dennis Sullivan, is what is a relationship. There is not a categorical relationship, it's not a categorical how to say statement about things. It's more like a framework only. And so I have to compare. I'm going to compare both things mainly by using figures, so you can get the idea of the topic. But at least there is one thing which is common to both, which is the Riemann sphere, denoted by C hat, which, well, everybody knows it, but I would like to introduce as CP1, the complex projective line. And so, I don't know if I say, all of you are familiar with the complex projective line? Yes? Mm-hmm. And so you take C2. I like to watch it as C2. So you take C cross C. Any point in C2 is a couple of complex numbers. And you take the lines in this space, complex lines. So if you take a point CW and you multiply by lambda, with lambda in the complex, you create this complex line. And then you take off the 0, so you take C squared minus 0. And then you divide, you take the space of lines, and this is CP1. And yes, we have two objects here. The object at the left is the automorphism. It's like in Shirley's talk. we have a space and a group of diffeomorphisms acting on the space, or a Lie group acting on the space. In this case, is the automorphisms of CP1, and in this case are the endomorphisms of CP1. And I'm going to describe these objects in the following way. You take a map here, a linear map from C2 to C2. You can distinguish as a matrix, complex matrix of 2 by 2. And so CW goes to AC plus V. I mean, I'm writing a complex, linear map from C2 to C2. And if you project, there is a function which goes from this space to the complex line, which is the projection. We can choose a chart, for instance, if you take the line at base on 1, this is a C line. It's a parallel to the horizontal axis. And so each of these complex lines touches in one point that line. So this is a complex line, and except for this one here, which is the infinity. If we choose that chart, the projection will be, let's say, of this form. So to any couple here, send it to the quotient, and the lambdas cancel, and you see that this is well defined over the complex projected line or curve. And also here, so we have this situation. But now, since this is the parameter, we divide by W. And so we have here C, W is 1, W is 1, and we recovered these automorphisms of the sphere. So this is the left-hand side here. So these are the really Möbius transformations. Immediately we see that if we look for automorphisms of the line, we ask the infinity to be fixed, and so these are the affine, the subset of Möbius transformations which are affine. That means that are of this form. This fixes the infinity, and so this will be the automorphisms of C. And endomorphism of CP1 is when you have, you see these are polynomials, homogeneous polynomials of degree 1. So then we choose homogeneous polynomials of any degree, and we do the same trick. And so the result is that if we have a polynomial, homogeneous polynomial of this degree n here, and another homogeneous polynomial of degree n here, we have the quotient as P of C divided by Q of C, and these are polynomials, and these are rational functions of the sphere. So these are in reality the rational functions of CP1, which are quotients of polynomials. And now, what do we do with that? Well, this is the left-hand side of the dictionary, and this is the right-hand side of the dictionary. So this is rational dynamics and Kleiner groups. So what is the relationship? So let me explain a little bit more about Kleinian groups before watching some more images. And so you can see that, this corresponds to Kleinian groups, which means is that a Kleinian group is a discrete subgroup of Möbius transformations acting on the sphere, on CP1, on C. CP1 is the same thing. So that this automorphism goes in this side. The endomorphism goes in this other side. Now I'm going to explain what is this. So Möbius transformations are the set of complex matrices, so that well, you can see from the construction that if you expand and you project, you don't do anything. So you easily can see that the determinant of these matrices can be chosen to be 1. Or in other words, if you write down the transformation like that, and you multiply by the determinant or by some lambda, but everything cancels, lambdas cancel, so you can think that the determinant is 1. So that means that the group and A, B, C, D are complex. So you have the linear group of 2 by 2 matrices with complex coefficients, determinant 1. And also, if you take the identity and minus the identity, is the same Möbius transformation. So you projectivize, and this is the Möbius group. This is equal to a Lorentz group. With T, and it's the component of the identity of the Lorentz group. I don't know you. So that are the orthogonal special group of the metric 3-1 that Federico likes to work with. Okay, so this is a Lie group of dimension real. It's a complex group of dimension 3. A real Lie group has six dimensions, and the topology is the topology of the coefficients. You move a little bit the coefficients, you move a little bit the points, and so that's the topology. And you take subgroups which are discrete. So this is like having points in this space, well, in this group. So I'm going to make an example to make it easier. So Möbius transformations, as you know, are classified and send circles and circles, and etc. All that. And a conformal preserves angles between tangent vectors and all that. So well, if you write the Möbius transformation like that, and you look for fixed points, for instance, you equal this to C. That means that C goes, this is the image of C under a Möbius transformation, and you want to find out fixed points, you solve this. This is a quadratic map, or you write it like that. Complex quadratic maps always have solutions that can be 2 or 1, but always have. So you have 2 or 1. So imagine you have 2 at this moment. So choose a matrix transformation with 2 fixed points. Preserve circles. So you can imagine that I preserve this circle. And now what? You take an orthogonal circle, like this one. This orthogonal. Since the map is conformal, has to go to another orthogonal circle. Circles goes to circles. So and that one to another circle, and to another circle, and to another circle. So this is the orbit of the yellow circles. This is backwards, forward, so you take really a group with certain generators. A1, A2, these are matrix transformations. Finite group. And they act by taking them, the inverses, and all possible combinations, multiplications of these matrices are matrices as well, and so are matrix transformations, blah, blah, blah. And so here I am, I took one of these maps, one element here, and assume that has 2 different fixed points and gives this dynamics. So the dynamics moves points in this way. So we put some arrows. And also here. And also preserves the orthogonal family of circles, which maybe I'm going to write in red. These are a family of orthogonal circles. And so you see the flow it's not a flow, it's a discrete map. So the points are jumping, but jumping this way. And there is something called fundamental region, which is one of these objects here, like that, these shapes. And you can think in what is, you see you have here a disk, and you take the action by gamma. So it means it's generated by gamma because we are taking powers of gamma, and you take the quotient by the action, which is this fundamental region with the boundary glue, because this line goes to this line. Also, that goes a cylinder. And so, in general, these actions give description of surfaces like that, which are called Riemann surfaces. So it's interesting because in this way one obtains all Riemann surfaces. It's the uniformization theorem of Poincaré and Coebe. But now what we are going to see is the action of a group with 2 generators, gamma and delta, let's say. And let us choose delta such that fix a point here and send this line to this line. Exactly. So these are orthogonal, and they are tangent in these points, and we have to complete the diagram. So now our fundamental region is this square, and it's sent to, you see this curve here by the first map is sent to this curve, and to this curve, and to this curve, to this curve, and so on, and so on, and so on. So we are if you complete our backwards, we have this construction. And now we have to use the other generators, the other generator, and to move these points here. And so you will have a drawing like that. Well, more or less. Perhaps you have seen these drawings many times. And the quotient by the action is, we have to identify this curve with this curve, and this curve with this curve. But they have this thing, I don't know how to call them, cusps. And so the quotient by the action of the group with two generators is something like, you can imagine it's like that. I don't know if I'm explaining it right. So discrete, as I said before, discrete subgroups corresponds to Riemann surfaces, which can be like this one. And so that's this side. Perhaps if we see some images, that picture is here mathematically constructed. So you see the square in the middle, and then more or less one can see the iterations with different red colors, orange, red colors. And points here iterates and tends to the boundary of this figure, which is the circle or the boundary of the disk. This is called the limit set of the action of the group. It is denoted by a lambda of the group. This is limit set of the action. This is another famous subgroup, which is the modular group. It's generated by two elements, S and T. S of C is equal to minus 1. C minus 1 over C. And T of C is T plus 1, C plus 1. Yes, this disk is represented as an upper half plane. It's the same thing. If you compactify adding the infinity, you obtain this disk. So it's the same object, but it's easier to represent the group here. It's a translation. C plus 1 is a translation. This band here goes to this band and goes to this band by T. And the inverse goes to this, etc. And S is like a rotation. 1 over C is a rotation. And then minus. And it's, the fixed points are the I and minus I. It's a Mévis transformation which rotates fixing I and minus I. And so since the, how is it say, the dark or the lined shaded line, thank you very much, shaded line to S, and so on. So this describes the different figures that appears under the action of this group. And so what, okay, so. And the limit set, as you see, are the limit of these regions, which tends to the real line. So the limit set is again the real line, which is the circle, if you think this is a disk. And so here what's happened is that the coefficients of the transformations are real. So we are working with subgroups of PSL2C, but with real coefficients. And in fact, the coefficients are integer numbers. So this is the group which is denoted by that. Since the coefficients are integer, this is the same as this one, that one. The ones that preserve the reals, these preserve the real numbers, the real line. If you write down here R, this transformation preserves, everything is real, so sends reals to reals. So those are called Fuchsian groups. So these are the real version of these Kleinian groups. What's happened is that Poincaré was studying these groups, and another guy called Fuchsian was studying Fuchsian equations, differential equations, and Poincaré saw that the symmetries were given by these Fuchsian groups, and so he called it Fuchsian group. Of course, Klein was working at the same time in the same things, and he protested to Poincaré, why you call that Fuchsian? What? You are forgetting me. And so he called all the other ones Kleinian groups, so that everything was on peace. This is another construction. The arrow says which circle goes to which circle, and so on. When you glue, that's the fundamental region, and you can imagine here all the others. Orbit of that fundamental region around. The limit set is this circle. And the quotient is a genus 2 surface. That means it's something like that, like this. And so you can make many constructions. That is the surface. And here. This is the left-hand side. So allow me to explain the left-hand side.
Excuse me, but this is conformal, no? The all this, the genus. How is the relation between the genus of the surface and the number of generators?
Good question. What's happened is that if you think in the Fuchsian groups, for instance, Fuchsian group case. So the space where you act is the disk. So the automorphism of the disks are really this group. It's the same but with real coefficients, because preserve the reals. And this is in fact the universal cover of all these surfaces. So you have the projection on there, and some discrete subgroup acts here and gives the surface. So this is the universal cover. So naturally, pi1, the fundamental group of the surface S, is gamma. It's isomorphic to gamma. So this has 2, 3, 4 generators, this group as well. And in this case, the generators are that ones. You fix a point, and M1, M2, L1, L2 are the generators. So when you cut through those lines, they split in two, and those are the gluing maps. So A2 glues with A2 prime and gives one of those curves in there. So you can count.
This surface is provided with a complex structure.
Yes, because the disk has a complex. Well, the disk is embedded in the Riemann surface. Sorry, the sphere, which has a natural complex structure. So this as well. So these are acts. The discovering of Poincaré is that this group acts by isometries and acts by conformal maps, because are Möbius transformations. So this is isometric to the disk, and at the same time it's conformal to the disk. So it's fantastic in some way. So what's the time, by the way? Okay. So I'm going to explain what means that circle, black circle now, which is situated here. So now we have to take an endomorphism of the Riemann sphere and obtain that circle there. It's quite similar to this one in the dictionary, but not in the action. So, a good example of Riemann of rational map is, for instance, c squared divided by 1, so c squared. And now we have to iterate c squared. Iterate. So in other words, it's the generated dynamics generated by f and its iteration. So we have to consider f followed by f, which is denoted by f2. It's not square, it's the composition map. And so on, f followed by f, and so on. And f to the n, and so on. So we have to see what's happened when we apply this map to the points. And so the orbit of a point, C0, orbit of C0 under F, is the image of C0. Well, we have the identity and the iterations. So it's C0, F of C0, and so on. And that's the orbit to the future. We have orbit to the past, but here it happens that since the polynomial is the rational map is of degree 2, we have 2 images for each iteration at the past. So the drawing, if you want, is something like we have C0, then F of C0, and so on. But in the past, this comes from 2, and this from 2, and this from 2, and so on. Something that doesn't happen in Möbius transformation because Möbius transformations are 1-to-1. Here it's 2-to-1, so we have that situation. Okay, so let's see what's dynamic here. So this is the complex plane, and the origin goes to the origin, and it's the unique critical point, as we surely talk, and it's of well, geometrically, any angle here is sent to the double of the angle, because C is RALI phi. You describe it in those coordinates, polar coordinates. C square is R square e to the I 2 phi. So double the angle, and the distance to the origin squares. So if the distance to the origin is less than 1, points tends to 0, and moving around because the angle doubles. So we sign, oops, no, like that. Yes, they are going around in this way until they end at 0. So 0 is an attracting point. Then it's an attracting point for every point inside the disk, because that's what's happened to any point in the unit disk, exactly. So this is the unit disk. And outside the unit disk, everything goes outside, also rotating, but goes outside. So that's the duality in this figure. White color means the points goes to infinity, and black means the point its orbits stay bounded. It's the duality, and that's the way they draw the figures. And now you move the parameters, you perturb, and so you choose maps of this form. So you add a new parameter, you perturb, and if C is 0, is this example, is the left, upper left figure, while you put 0.20, I think it should be negative, 0.25, but that should be negative. Is that figure. So when you write here minus 0.25 gives that figure, and so all those are in the negative side. With the minus, yes, exactly. Isn't it? Yeah, and so on. So this is a perturbation of the original map. And so I wanted to explain, but I don't think I have much time. Where does that perturbations come from? We better look at the images. These are the same drawings, but with a group like this. Oops, like the one I have of this square, but perturb. We perturb, or you perturb the coefficients of the numeric transformation, and you obtain the disk moves and takes those shapes. And inside is the square and all the iterations somewhere, somehow inside. This is an example where you see the square, you see, and the perturb. So the disks, the circles are, you see, one bigger, another one smaller, and so on, but all tangent. That's the only condition. All tangent. And you take the action of that group, and you obtain this figure. Perturb coefficients, and this is a limit of the perturbation. Because now the squares now are triangles, you see? Something changed, it's a bifurcation there. Let me go a step before. Here the limit set is the black line, because everything tends to like accumulate there. And so it's a fractal curve, has a certain house of measure and so on. So one has to discover what's happening with the Hausdorff dimension on these fractal curves, on the limit sets, and in these cases as well, and in this case as well. So this is the limit of the deformations. This is in the border of the space of deformations, which is called the Teimuller space. And so the technique, well, this is on the technique of how to prove those things, called quasi-conformal maps. And so I'm not going to talk about that much, but that's the idea. Are homomorphisms that deform the surfaces in a bounded way. So these are deformation of a bounded way, in a bounded way. But it's important because those mappings, quasi-conformal maps, are important for people that study images, faces, or recognition of figures in computing. So that's the idea. So quasi-conformal maps deform circles to ellipse in the infinitesimal way. So that's the idea. And there is a calculation here how to do. And mu is called the Beltrami differential. And so, well, these are, when you apply these differentials very much, you obtain this limit set of the same object, the same group, the form. This is a deformation of a map, of a square map. So this is on the other side of the dictionary. And this picture comes because, I put it because it's a historical picture, appears in a book of Fricke and Klein. Yeah, so it's 1880 something. And they are constructing precisely these deformation structures, as you see. There is a square, how was it, shadowing square and shadowing triangle. And the limit sets, they are trying to figure out what's the limit set. And so if we do this thing now in computer, we obtain the following thing. These are the first steps. You see, these are the circles where we have to move. There is the square, the triangle. This is the reflection. So we obtain that figure, and so on, and so on, and so on. So next step, and so on. So this is exactly what they were reproducing. So it's very, very nice that they did it right somehow. And this is precisely the time-Euler space of those figures, of the deformations of that group. This is where you move is, you see, you obtain different structures on the surfaces, on the quotient surfaces, and as you move towards the boundary, this is the boundary of the time-Euler space. This is a special situation, and the problem is what and how you get to these boundary points. So there are very nice studies of how to do that. And that's it. This is an application of the theory to something concrete. And that's it. So, yeah, I think that we finish here. Next time, if you come, we can see how these things evolve nowadays. Because this theory was developed in the 80s. And now there are new developments that we can try to see figures and pictures of what's going on, if you want. But thank you to Federico for inspiring so many things in the faculty. He's a very nice friend, and we are very happy to have him here. And nice. Happy birthday.
Do you have any questions or comments?
I have a question.
Yeah, sure.
People here, there are a group who works on submanifolds, remaining submanifolds, and you have this construction which is not really a submanifold. I mean, for instance, the case of the double torus, okay? That has a complex structure.
Yes.
Okay. Do you think it's possible to immerse something like that, an Nash theorem, but in the projective space, in CP3, with this?
Well, there's a theorem since Poincaré that all these Riemann surfaces comes from polynomial equation CP2. So you take a polynomial in two variables, you equate to 0, you solve it, and it's one of these objects. But you can immerse them in any CPN, because you can embed CP2 in CPN. But maybe you want some more structure, like minimal surfaces or something like that.
It sounds interesting because see, if you can do that, you have properties of submanifold. For instance, curvature lines, and asymptotic lines, and all this kind related with dynamics, because what you're doing is dynamics, and the conformal structure comes from that. And I don't think this problem has been studied. And to me, it's interesting. For instance, Vinicio and we were working on the description of some foliations of the torus in C3 included in R4. You know? This is CP2 or something like that.
Well, we have to see, but it sounds interesting.
Yes, you have to make the compactification, whatever, but you have an ambient space.
Exactly.
Where you have relationship between this conformal structure with the ambient, the complex ambient.
That's very nice.
And
yes.
that makes sense to study.
Yeah, it appears in many fields. For instance, in string theory, the atoms or the elementary particles supposed to be strings. So when they move on time, they describe a tube, a Riemann surface, but those things also, crash with an electron or something and then divides into joins again and things. But that's a Riemann surface. So in string theory, Riemann surface, and that's in the space-time of string theory, which has 10 dimensions. So whatever, that you can do many things, yes. But what you are doing perhaps is very interesting. Mm-hmm. But the natural space is CP2 because this polynomial thing. Mm-hmm.
Two complex dimensions.
Two complex dimensions, exactly. For real.
Yeah, for real, yes.
Mm-hmm. R4.
Yeah.
Mm-hmm.
Compactified.
Compactified. Mm-hmm.
Okay, let's thank again Guillermo.